Now, the next thing we want to talk about are force diagrams. How do we draw out force diagrams? So a force diagram is always going to be associated with an object. And so I might be talking about a book sitting on a table. If I want to, I can draw a force diagram for the book. I can draw a force diagram for the table. I can draw a force diagram for the floor, but I have to draw a force diagram for something. And then what we'll do is we'll draw all of the forces acting on the object. Now, it's very important that we learn to define forces. And when I define forces, I'm going to talk about what type of force they are. So recall from here, these are the types of forces that we'll be talking about. Gravitational forces, normal forces, tensions, compressions, and friction. Those are the forces that we'll be talking about. There are other forces generally associated with either normal forces or friction when you get down to the subscale. But these are the 5 forces that we'll talk about during these lectures. So when I define forces, I'm going to talk about what type of force I have. Then I'm going to say what that force is due to. This is a very important process because it's very easy for us to think about forces as we've imagined them over the last 10 to 20 years of our lives or more. And we're interested now in being very particular. We want to be very physicist in how we look at these forces. So forces must be due to something, and that something must be physical. You can't have a force because of an action. There might be an action associated with a force, but there has to be something causing the force, something. Even if I talk about a long-range force like gravity, gravity is caused by the Earth. That's a physical object. So as I discuss forces, I'm going to always define them. I must give a due to, and there has to be a physical object that's exerting that force. And then I'm going to state what that force is acting on, or acting upon. That might be more proper, but I'll say acting on. If I'm drawing a force diagram for the book on the table, all of the forces that I'm talking about will be acting on the book. If I'm drawing a force diagram for the table, all of the forces I'm talking about will be acting on the table. So if I have multiple objects, pick an object, draw the forces acting on that object, what are they due to, and they'll all be acting on that object. If there's another object involved, then draw that force diagram separately. So we've been talking about a book on a table. Let's take a look at a force diagram for the book on the table. So there is a gravitational force acting on the book. So I'm going to label that mg. You always want to label your forces. And I'm going to define this then as a gravitational force. So I want to write these out so I know what's going on. A gravitational force due to the Earth. All forces have to be due to something. In this case, it's the Earth. And I'm drawing a force diagram for the book, so this is acting on the book. So there is my force definition for gravity. Then there's an upward force, and that's the normal force. And I'm going to label that F sub n. I don't want to label it n because that would confuse it with newtons. So I'm going to label it F sub n for normal force. So I define that as the normal force. It's got to be due to something. Well, it's due to the table. That's what's exerting the normal force on the book. And then this is still acting on the book. So there are the forces acting on the book. And there are 2 of them. Now there's no force acting to the right or to the left. And if you look at this, there is nothing touching the book except the table. Remember, the only long-range forces are gravity. That's really the only one we'll be talking about for quite some time. The electromagnetic force and the electrostatic force. So we're not concerned with electricity or magnetism here. So the only long-range force is gravity. We've accounted for that. And then short-range forces require touch. And the only thing touching the book is the table. So only the table can exert short-range or contact forces on the book. Here's a ball that's in flight after it's been hit by the bat. And just for the sake of argument, let's assume it's flying up and to the right. So this is the direction of the velocity. Not the acceleration, this is the direction of the velocity. And we're going to ignore air resistance for a moment. So there's nothing touching this ball except the air. Again, we're going to ignore that for a moment. So the only forces acting on the ball must be long-range forces. And again, there's no source of electricity or magnetism. So the only long-range force I need to concern myself with is gravity. So there's a gravitational force acting on the ball, and that's in the downward direction. That's it. There are no other forces acting on the ball. The bat has already hit the ball, and it's left the bat, so the bat is no longer in contact with the ball. And the motion of the bat, or the fact that the bat hit the ball and sent it into motion, does not allow a force to be acting upon the ball. The ball is a body in motion. It will remain in motion unless acted on by an outside force. So as you consider projectile motion from the last chapter, the ball is moving in an arc, and the reason that that straight line is not continuing is because of gravity. So the velocity, especially in the y direction, is changing, but the x velocity is not. The x velocity remains to the right with whatever value it had. That will not change. Now here's a situation referred to as a modified Atwood's machine. We have a mass hanging over here. I'm going to refer to that as M1. And another mass on the tabletop, I'll refer to that as M2. And you'll see this in one of the accompanying videos. And then the two masses are attached by a string, which you see here and here. And I want to draw force diagrams for each block. So let's start with block M1. Now I like to draw my forces in blue, so there are two forces acting on M1. First, there's weight, so M1G, and this is a gravitational force, which I'm just going to label gravity, and it's due to, and I'm going to use dt for due to from now on, just shorthand notation, and that's due to the Earth, and it's acting on block 1. So this is a force diagram for block 1, and there's the gravitational force due to the Earth acting on block 1. The other force is tension T, and that's a tension, and it's due to the string, or due to the rope. I'll say it's a string. It's due to the string acting on block 1. So there are these two forces. Nothing else is touching the block, so there are no other short-range forces, and the only long-range force at play here is gravity. The tension, because it's due to a string, can only be in the direction of the string. And since the string is in an up-down direction, and the string cannot push, it must be a pull in the upward direction. So those are the two forces acting on block number 1. The tension due to the string, and gravity due to the Earth. So here's block 2. Now I know there's a weight, M2G, so again that's the force due to gravity, and that's also due to the Earth, and that is acting on, in this case, block number 2. And then there's a normal force because the block is on a surface. Could be the track that you might see in a video, or it could be a tabletop. So there's a normal force. I'll label it F sub n. And again, that's a normal force, and that's due to the surface, which I'm just going to label as a table, acting on block 2. Then recall the string was moving to the right. Okay, so you see the string right there. So that's a tension. That's also due to the string. And that's acting on block 2. And finally, there may be a frictional force. Now the string wants to pull it to the right, and so a frictional force would be to the left. I'm going to use a small letter F for frictional forces. I'll talk about different kinds of friction later, so I'm just going to leave it as an F. And this is going to be a frictional force, so I'm just going to say friction. And remember, friction is due to a surface, and the only surface touching this block is the table, and it's also acting on block number 2. So we have a frictional force due to the table acting on block 2. So those are all of the forces acting on the block. Here's a similar diagram, and we'll look at a video of this as well. Again, let's think of this as block number 1, and this is block number 2. And I want to draw a force diagram again for each block. So here's block number 1. The force diagram for this block really won't change at all. There's going to be a gravitational force, M1G, and there's going to be a tension, T. I still want to define my forces. I want to get used to this until I'm expert at it. So there's a tension due to the string, and this is acting on block 1. And this is a gravitational force, which I'll just call gravity, due to the Earth, and this is acting on block 1. And here's block number 2. So now the gravitational force is still down, so there's m2g, so that's gravity, and that's due to the Earth, just like it always will be, and that's acting on block number 2. And then there's a normal force. Now in this case, perpendicular is in this direction. So the normal force has changed direction. So this is a normal force, and that's going to be due to the track. And that's also acting on block number 2. Okay, so acting on block 2. Then there's a tension. That's in the upward direction and to the right. So there's T, and that's a tension due to the string. And that's acting on block 2. And then there might be friction again, so there's a frictional force, so I'll label that friction, and that's due to the track, and that's also acting on block 2. All of these are acting on block 2. So there are the forces in this scenario. Now I just want to mention at this time, and we'll worry more about this in later lectures, but I want to think about what my x and y axes are going to look like. If I go back to block number 1, it's really not too difficult to have the x-axis to the right and the y-axis up. And we know that block number 1 is falling, assuming everything starts from rest. And so the acceleration of block number 1 is in this direction. So I'll label that a sub 1. So it's in the negative y direction. But for block number 2, things get a little more complicated. The acceleration of block number 2 is going to be along the track. So there's acceleration 2. And so this begs the question, what direction is my x and y axis? Now I can make x to the right and I can make y up, just like I did for block number 1. But if I do that, then I need to break the acceleration down into its x and y components. And I've got 3 forces, 1, 2, 3, that are acting either along the incline or perpendicular to the incline. And so it makes sense for me to rotate my axes so that the x-axis is along the incline and the y-axis is perpendicular to the incline. I don't have to do that, but this is going to make my mathematics a whole lot easier. So I recommend in most cases here that you align the x-axis with the incline and the y-axis perpendicular to that. There are very few exceptions to that rule.